I also want to say welcome to everybody. As mentioned, I work for Cray at HRLS, so I do application support there on all the problems and issues users have there, starting from compiling their code up to profiling, debugging, and also optimizations. And yeah, in that presentation, I want to introduce you to the OpenMP device constructs. So as I saw in the last presentation, most of you are already familiar with OpenMP directives, right? No? Who not? Okay, good. So that fits quite well to what I prepared. So I just want to give you a kind of a short introduction, motivation, why to use these directives, and then I want to go slowly introducing a first kernel, then also data scoping and data regions. I will do within my presentation a kind of a general view of OpenMP and OpenACC. So in the examples I will show, I will do each on a slide. So I have slides for OpenMP and slides for OpenACC. So depending on what you're interested in, you can afterwards go back to the slides and have a closer look. At the end of the presentation, I will also have some comparison about the different pragmas for both types. So why to use directives? It's a simple and easy use method. So these are, from a programming point of view, just comments in your code which should then lead the compiler to do the actual optimization for you. So these hints, so-called pragmas, are added then in the code, and depending on how you select it during your compiler, they will be used or will be not used. You can switch on and off. You could also use pragmas for OpenMP and OpenACC, and then maybe decide which one should be used from the compiler, and so on. As mentioned, these directive-based programming models are easy to use, so there are just quite often a few lines of code you have to add to port your code. I mean, depending on your code, getting more and more for sure. They aims to be portable between different hardware architectures. We already mentioned it. Since they are easy to program from that point of view, they are also easy to maintain, since you have, compared to low-level models like CUDA and OpenCL, you have just fewer statements, so you can more easy adapt them and also tune them. And yeah, and in contrast to that, usually the trade-off is the performance, but I would like to mention that especially with the newer implementation of these directives, the difference to the low-level implementation like CUDA is not that large anymore. So you could most times expect, I would say, up to 80% of the performance of a low-level implementation like CUDA, but with much less effort. And that's how I also would like to start. So I would like to do a short example. So let's say we have a a simple reduction function. So we have a loop here which does a summation of the elements of an array. In that example, I use a Fortran one. And if you perform that one just on a CPU, we get, depending on the hardware we have, but let's assume, this is a quite old example, we get 2 gigaflops on a pure CPU run. Then, you could also think of implementing this example in a CUDA implementation. if you do it a trivial one, you end up with, let's say around 31 lines, and at the end, you get 1.7 gigaflops. So the performance drops down since you maybe did not the perfect tuning for your hardware and so on. So yeah, you could also put much more effort in that and do more tuning. I know it's far too small to read it, but just to give you an idea. So with more tuning, you then end up maybe with 50 lines, but then your performance is significantly improved by a factor of 5. So in contrast to the original CPU version, we have now 10 gigaflops, which is quite nice, but you have to put a lot of effort to port your code to CUDA. So now we want to do that the same with our directives. So we again start with this simple code here, and then I will come in more detail to the actual directives meaning. We add just this one directive, which means that we want to distribute that on the GPU, and you need to mention that this is a reduction. So we have basically 2 lines, one at the beginning, one at the end, one statement, and nicely we see we end up with, in that case, this is really all, we did that on a Fermi, so this is quite some years old, maybe on the Pascal we would be even much more faster, but just to get you an impression, we end up with 8 gigaflops. So what the compiler then does for us, and I mentioned already that these statements are just hints for the compiler, it splits up the code from the serial part. So here we do initialization on the CPU. Then we have a part which should then run on the GPU, which is then namely this kernel here. And then maybe at the end we do some more stuff on the CPU, writing files, printing out something, and so on. So the compiler divides the part of your code into a serial and the parallel part. It also keeps track on data movement, so the compiler manages the data to copy that to the GPU and at the end copying back and so on. So to give you a short overview about the accelerator directives, they are more or less as old as the low-level implementation. So in 2007, the CUDA was the first CUDA version was released, but also the HMPP, which is also a high-level directive model, was also released in 2008. The OpenCL was released, but also here all the green ones are the high-level ones, and the 2 blue are CUDA and OpenCL. And we see there, I didn't print up the development of the low-level ones, but we see there were more and more different models and versions available. So where we are now is that we have OpenACC 2.5 and OpenMP 4.5. So these are the actual dates where the standard was released, and then there's another story when this is implemented in the compiler. But usually this occurs some few years later, let's say like that. Short overview about that I have here on that slide. So I compare here OpenMP and OpenACC. Kind of a short history. So OpenMP with the first host parallelization was released in 1997, and then there was also the device construct implemented in the OpenMP 4 version in 2013, which then got within the crazy C compiler 2016 in full support. And now we have, now we have OpenMP 4.5, which will be available the full, in the actual Cray CC 8.5, we have on the machine we use here, Daint, available. The OpenMP 4 is supported, but there are some exceptions which are not implemented yet, and in the next version, 8.6, which will be released in June, July this year, the full OpenMP 4.5 is supported. And on the other side, OpenACC was announced at Supercomputing 2011, and then also implemented in different compilers, Cray, BGI, also CAPS. And yeah, what should I mention? We from Cray decided to now concentrate more on OpenMP, and as you will see, the gaps between the different specifications gets closed, so they are really can do both more or less the same features, but there are still some more development in OpenACC driven by the other contributors like BGI. They also implement then the OpenACC 2.5 versions and maybe also later versions. So when you want to start, you need maybe to decide what to choose, OpenACC, OpenMP. I would like to mention that they are really similar and you can easily swap from one to each other. You have to change your statements, but the functionality based on that is quite similar. And OpenMP, from a more general point of view, aims more for programmability. So they also aim to be more general definitions for different hardware, so it should be also more portable to different accelerators. And in contrast to that, OpenACC was really specified for a certain hardware, so it's really focused on directives for special accelerators. So this is also a more descriptive approach to this parallel programming, while OpenMP is more prescriptive, so that we say, okay, we want to do a certain functionality and then the compiler needs to transfer that somehow to our hardware. Yes, as mentioned, there are really similar ways of exposing this functionality to the hardware. What the compiler is necessary to do is to take care, that's the most trivial, the most complicated way is really to handling the data management, and as you will see, this is kind of the bottleneck, and therefore you need an information about the data locality, which you should, the compiler can do that by itself, but most often it's helpful if you, with the directives, give the compiler some hints how to do that. Yeah, and the hard work is really to get this information, so not always the compiler can do it by themselves, so then it's up to you as a programmer to specify this data locality and check if the compiler is doing right, or providing that to the compiler. If you want to start with OpenACC, for example, it's quite easy then to port your code also to OpenMP. So as I mentioned at the beginning, maybe it doesn't matter which of the both you choose, you can easily swap to the other one. Yeah, so to repeat, they are quite similar, and they are OpenMP is used to be more widely supported, maybe also in the future for more or different hardware architecture. This I cannot say what development there will be. OpenMP, from my point of view, develops quite fastly. So with the previous standard, there was quite a huge gap between OpenACC and OpenMP. So much more functionality was implemented in OpenACC than in OpenMP. But now, with the newer 4.5 version, we're getting really close to each other, and then the difference is so small that it should not matter that much. So my advice is select one, but the crucial thing is really to understand your data locality, that you implement that one, and then you can also change easily. So as I shortly mentioned, if you, for example, implement your first kernel here around these double-nested loops, you specify just for the compiler that you want to parallelize these loops, and then the compiler takes care about the memory management, so which data should be transferred to the GPU and which memory needs to be transferred back to the CPU again. It also takes care about the loop scheduling, so how the loops should be divided in thread blocks and thread within thread blocks and so on. And the compiler also takes care about synchronization, so that at the end of these loops, all the threads are synchronized and the memory is handled well. And yeah, data movement and memory management is to allocate it on the GPU, and data movement is to copy. So yeah, maybe let's start with the first example. So in this example, we have two loops, one initializing an array and the second loop then operating on an array. Here just to multiply by 2. It should be really a simple example to just show you the functionalities. And we want to do both of these loops on the GPU, so we want to start there 2 kernels, which also handles for us the synchronization between these 2 kernels. And for OpenMP, we just do the OpenMP target team distribute statements. So target just means that you want to perform this calculation on the GPU. Teams creates leagues of teams. So in CUDA, we call it a grid of thread blocks. And then distribute means that all these, the whole loop should be distributed then within the different threads. This is the example for Fortran code. So for C and C++ code, it looks quite similar, but there we do not need, we have no need to, do the close pragma, since we have our structured blocks anyways here. In OpenACC, it looks similar. There we specified with the pragma ACC parallel loop. And we do similar as OpenMP, we do the end parallel loop statement. And yeah, similar to OpenMP, the parallel just creates the gangs of workers, we call it, with OpenACC, which is again the grid of thread blocks in CUDA. I mean, it's related to that one. And the loop just, again, tells the compiler that the following loop should be distributed over the threads. Same example for C++. So we just do not need to take care about closing of the closing statement. But another important thing is about data scoping. So when we have our code with parts which are serialized on the CPU and parallelized on the GPU, and we need to transfer data. We have to take care about how the data is transferred, and then on the parallel side, so on the GPU side, we also need to take care about how the data is shared or private within the threads. So we want to avoid race conditions so that multiple threads act on the same data in a manner we don't want to. So we need to take care about, especially about the shared data. And then we also have to think of synchronization. So as already mentioned, the global synchronization will just happen at the end of our kernel here. And so in contrast to real serial code, where on our CPU each rank has its own data, even with the OpenMP host parallelization, we already have to think about sharing data and there also the data scoping. We do similar things here on the GPU. So we have to think of which data is private. For example, the iteration counter in a loop. They differ from thread to thread, but maybe different threads works on a huge array on different portions, so then this array could be shared. And as mentioned, a correct data scoping ensure that your program execution or your result stays correct at the end. So even in a parallel execution, you want to get the same result as you would run it in a serial way, right? So, as mentioned, we have to understand our data scoping. We have to distinguish between shared and private data. Usually shared data are arrays we want to share between the different threads, and private data are quite often, especially the loop counters. And then there's a third part which is called the first private. So this is a variation of the private clause, which means that all the different threads have the same initialization of these variable. And as we also do in OpenMP host parallelization, we also have to take care about reduction variables. So if we have shared variables, which then at the end combines together between the different threads, which is called reduction, we have to specify that, especially with the directives to the compiler, to really take care about that. The reduction can be different things like summation or max-min value. Summation also includes difference, a subtraction. Could be also a logical operation, for example. So, as mentioned on the accelerator, it's similar like the host OpenMP parallelization. For the shared variables, we also have to classify them if they should be read-only, write-only, read-write, or scratched. So if we need to copy them to the GPU and copying back, or just need to copy it to the GPU and don't need to copy back, or the other way around. So this is how we implement or how we used it with the OpenMP statements. So we define them as private, first private, or reduction, and then we have these so-called map clauses, which then defines if we want to transfer data to the GPU. This is what we do with the map2. With the map from, we say, okay, we just need the result back from the GPU to the CPU. With the to from, we do both. So we copy first at the beginning the data to the GPU, and at the end of our kernel, we're copying back. And then there's also the so-called scratch data. We use the map alloc, which we usually just use for temporary variables on the GPU. So we allocate some memory there. We can handle there some variables, but at the end, we do not need to copying back. So it's just scratch. I come to that in a second. Yes, there is. The question was, is there in default? Yes, there is in default. And usually the compiler will be quite conservative. We will see in the next session how to monitor what the compiler does. So then we can check and verify. But yes, there is default, and I come to that in a second. I mean, here is the general rules. That's more or less that's the default. So arrays in principle are shared variables. So loop variables and limits are private or first private, depending on that. And in OpenMP, all scalars are now in 4.5 first private, but in 4.0, what we use here, it's shared. So this is what you have to be a bit careful about, since that will change in the next version. And if your question relates to the data transfer, so for the shared variables, if that will copy in and out, usually the default is that it will be copied in and out. And to reduce that overhead, we will come to that later. So a short example of OpenMP. So we create again two kernels. We already did that first line here, but now, since we know we do a data initialization in the first routine, we do not need to copy data in the GPU for that array. We just want to copy the data out of the GPU at the end, and that's what we state with the map from class here at the beginning. While in the second loop, we need our initialized data from the first loop within this kernel, and we want also the result of the computation back. So that's why we then just use the map to from clause, so copying in and out. Yes?
Obviously, between two loops, it's not necessary to copy data from GPU to CPU and then copy it back from CPU to GPU. Will the compiler optimize this, or there are some directives which allow to instruct it explicitly?
Yes, we will come to that in a second. Yes, you are completely right. So the question was, in principle, we have no need here for copying the data out of the GPU and then directly copying in at the end. You're completely right. From a trivial point of view, the compiler just will do this copying here just to be sure. Yeah, we want to prevent that, and we can do that, but I need some more slides in between. So for OpenACC, it's quite similar. We also have, again, the private, first private, and reduction clauses for private variables, and we also have for the shared variables, the copy in, out, just copy and create statement for the scratch. I here note these P copy in, P copy out, and P copy. So all these P statements stands for present or copy in, copy out, which means that the compiler will check if the data is already on the GPU and then do not copying the data. and if it's not already on the GPU, it's copying the data. And this is the same behavior what OpenMP also does. So if you do this data scoping within your kernel definition or data region, we come to that later, it always checks if the data is already on the GPU, and if it's there, it's using that one. So if you modify your code, if you improve your code, if you add more data region and so on, you can leave these data scoping in here, and don't be afraid that the compiler will overwrite the data with the one you stated here. So if it's always a present or clause in that case, like we use in OpenACC also. I mean, you can also do it explicitly. You can also say, okay, I don't mind if it's on the GPU. I anyways want to copying the data. Then you can also use the, for example, the copy in without the P.
There's a small remark here. I think, yeah, a small remark.
Yes, that's what
A small remark here from 2.5. The copy in, copy out behavior is present or copying. So
okay.
They are kind of now equivalent. So even if you have just copy in, copy out, it will just do the only one P copy in or P copy out.
Yeah, okay. So same as before, the example also with OpenACC. So I just added here the P copy out and P copy statement to our directives. Question to that? No? Okay. Then what we shortly mentioned, there are also data regions. So now you can also define regions where your data should stay on the GPU. In the last example, we wanted to have the data from the beginning of the first loop until the end of the second loop staying on the GPU and do not want to copying forth and back. And that's what we can do with the data region. So therewith we can avoid these extensively copying of data. Within this data region, for sure we have to keep in mind we then have two copies of our data. We have one copy on our GPU and we have another copy on the CPU. Between our two or more kernels, we can, for example, also act on the data on the GPU. So you really have to pay attention what you are doing there. If you need to synchronize your data between the GPU and CPU, this is not done automatically. It just tells the compiler to move your data at the beginning or the end of the GPU. Excuse me, at the beginning or the end of the data region. So one more thing to mention, this data region can also be nested. Yeah, one simple example here in OpenMP. So we have again our two kernels. We defined the data scoping here already during our implementation, but we realized there's a unnecessary data copying here in between the two kernels. So we added a data region around these two kernels, starting here at that line where we define, okay, since we initialize our data here, we just need to copy back at the end of the data region our data, and we just close it here afterwards. So we see that the combination of copying from the GPU back and here copying forth and back results in a just copying back at the end. So this kind of translation you as a programmer have to do yourself, that the compiler will not do for you. But in most cases, I would say it's quite logical what you want to do with your data.
This internal OMP map is still necessary, or one top OMP map will be sufficient?
Excuse me?
In your previous code, there was one OMP map for the region, map from A.
This one?
OMP maps, there is the OMP maps for every kernel.
Ah, right, excuse me. Yeah, good question. So the question was if these data scoping here within the kernel definition is necessary, right? Actually, no, they are not necessary here to specify them again. So you have an overall data region which defines that there is memory allocated on the GPU for that variable A, and you will not copying any data here. From my point of view anyways, if you port your code step by step, it makes sense to keep that definition in here, because we will see you can also use the kernels within different parts of your code than maybe the data region is called. And with that way you verify that if you call, for example, a function having such a kernel in here, but maybe not within the data region, still has the correct data scoping you specified before. So the compiler will neglect the data scoping you specified before, but I mean, if you have the data region around, but if not, you have to you already specified it, and so I would leave it in there. Yeah.
So in this case, they will be overridden by the top specification.
Right. Right. I mean, anyways, as I mentioned, this data scoping is like in present or case. So if the data is on the GPU, it always takes that one.
They have present or semantics of OpenACC.
Yeah, it's with OpenMP, it's always like present or.
I see.
But could you explain what's happening here? So we have somewhere array A, which was on the CPU.
Right. So you, as usual, you define and allocate your arrays on the CPU. Then within the first statement here, you define, okay, you need memory allocated on the GPU, and with the from statement here, you also specify that at the end of this data region, you need the values of these array back to your CPU. This is what the from stands for. And then you do your two kernels here, where these data clauses are neglected since the data is already there. And then at the end of your data region, the data is copying back to the memory on your CPU of variable A.
So the allocation on GPUs will happen somehow automatically to the same size.
Yeah, right.
And it will somehow also recognize the same type of area I had. Like if I had array of long doubles, it will make array of long doubles.
Right. I mean, we will see you can also specify just to copying subparts of your array if you want, just a half of that or whatever. So far, what is a problem is to copying a structure. So if you have a structure with maybe arrays in there, to copying the whole structure, that's still an issue. So you usually have to do it one by one yourself. But from all the types, so the memory sizes you do not have to care about that. The compiler does that for you. You just have to specify, I need that array on the GPU.
And once the data region ends, the GPU memory gets reallocated.
Right. When the data region ends, the GPU memory will be deallocated.
If now array A gets modified on the CPU between the first and the second loop, what happens when it?
Good point. I will do that in 2 slides. The next slide is the OpenACC example. So as mentioned, it's quite similar. We have these P copy out, so we want just the data back from. And again, we have these 2 kernels here with our data scope, which will be neglected. So what you mentioned, what happens if we want to do something on our host, on our CPU with these data here? For example, we want to print out something, or we do some modifications on our array here on the CPU. So we need a kind of an update here. And this is possible, so we can also define an OpenMP target update, and then we can specify in which direction the update should be done. But this is a good point. We really have to take care about that we have two data copies within our data region, one on the CPU, one on the GPU. And if we act of the lifetime of our data region on the CPU, we have to update that one. Just to mention, if we use the target update from, which means that we copying from the device to the host, and if we do a OpenMP target update to, we update from the CPU to the GPU. So it's always from the point of view of the GPU. With OpenACC, it's similar. So we have an ACC update, self, device, or host. So host is the same like self, and device means that you want to update to the device. This answers your question? Good.
Is it still effective to do that if you have A of I equal to 2 times A of I minus 1?
Excuse me?
If you had A of I equal to 2 times A of I minus 1, would you?
You mean here in that kernel? Or?
Yeah, inside, then you would have to update every time that you do.
But it perhaps cannot parallelize it in this case at all.
Right. If you have here a recursion, so a dependency of one array element on the other one, you cannot usefully, I mean, there are ways you can do it, but it's not that trivial. I mean, we usually want independent loop cycles that they can nicely transfer to the different threads on GPU. So as I shortly already mentioned, we do not need to copy the whole array. We can also copy subparts of the array. And there we have to pay a bit attention because that is different between Fortran and C, C++. So in Fortran, we really define the start and the end of our array. So we say, okay, array A, bracket from 0 to the 10th element, while in C we define a start and the length. I mean, in that example, it would be, I don't know, it would be different. It would be then 0 and 11 to going to the 10th element.
The previous examples were about Fortran. In Fortran there are true arrays, that is, array contains data and the dimension information.
Mm-hmm.
In C or C++, arrays are just pointers, so the length is basically not known. How would then these directives look in C++?
So if you want to transfer the whole array, it looks similar.
I have the array A, which
Yeah.
is just a pointer,
Yeah.
so the length is not explicitly known. Should
Right.
I then specify the length explicitly?
Yes. The question was in C, C++, the arrays are just pointers, and if we need to specify the length of the array explicitly, and the answer is yes, you should do. Now our advice is if you just port some parts of your arrays, you should be careful about doing that and not making mistakes. And you should then also use this tool I will show you in an hour with the profiler and runtime commentary to really verify that the compiler is doing that or transferring the data you really want to do. what you also should keep in mind that it's usually from a performance point of view much more efficient to have really contiguous memory parts, so array slices, and non-contiguous array slices then drastically reduces the performance usually. So up to now we saw that data regions, we have a start and an end, but maybe especially if we have a more structured code, we want to do that in maybe different regions in the code. We maybe have an initialization routine and a finalization routine where we allocate and deallocate our data. So that's what we can also do with the so-called unstructured data regions. So there we can separate the beginning and the end of the data region in different parts of our code, so in different functions also. So yeah, that's more or less in more details what I mentioned, so you really be able to separate that. As an example here in OpenMP, you then just specify the target enter data for the beginning of the data region and the target exit data of the end of the data region, and then you also separate that for the different variables in contrast to the structured data region we had before, where we really say, okay, we have n data region for our array A, which is then maybe just copied back. Here we can really say, okay, at the beginning of our data region we want to copy array A, or we just want to allocate some memory for array A, and at the end of our data region we then define, okay, we need to copy back, or we just deallocate, release the memory.
So the difference is the names of the variables were the same before, and now
yeah, the difference is that in the structured data region, at the beginning you state what should be done with the data, so should it be copied to the GPU, should it just be copying back, and with the unstructured data region you really say at the beginning and the end what should be done at the beginning and the end. So at the beginning it should be copied or not, or just allocate memory, and at the end you really define it should be copied back or just release the memory. Right. So similar in OpenACC, you also have the enter data directives with the pcopy in and pcreate, and the exit data with the pcopy out and delete statement. What else we can do? So here's a short example of that. So we have a data region within our main routine where we state that we need copying back the data. We have maybe a first kernel there, then we do a function call here in the main, which is within our data region, and then within our function you call double array. We have another OpenMP kernel, and we could add this data scoping clause there. It's not necessary, as I mentioned, but for example, if we want to call that routine from a different part of our code, which is maybe not within the data region, then we can be sure that the data scoping is also correct for that case. So it can then use the data there. It can, for example, also within this kernel call another function here called double scalar. And this is then the whole function double scalar is then implemented as a GPU version and then fully performed on the GPU.
in this code there is no variable C on the CPU memory.
It is, since we have transferred here in the main it's called A, so there we have to pay attention. It's called A, we're copying A to the GPU, then we call our function with that variable, which is then kind of renamed here in our function as b, but it's still the same variable, so the same memory, which is then used here within our double scalar function. So this variable c is an element of the array we have already on the CPU, so it's using that one. Yes. Questions to that? Yeah?
So we must be then aware which functions the GPU is able to handle.
What do you mean? Which function?
Like, can you take any kind of function and run it?
In principle, you could, yes, you can take any kind of function, run it on the GPU. The question is how fast that will be performed. I mean, I will come to that later on. So if you have a lot of branching within your function, that will perform not that good. But if you have a lot of same cycles, as Vasilos already mentioned, if you have many instructions on different, if you have a huge amount of data where the same kind of instructions are performed, and this is what we are going for, since we have these hardware structure with warps and, as a.
So even if the code is in the different compilation units, the compiler will still be able to.
So yeah, okay. If we call that function double scalar here within a kernel, and maybe from another part of our code in a non-accelerated part, there will be two different types compiled. So there will be one compiled for the GPU and one for the CPU, and then during runtime the one will be selected. Right. Good point.
So in this example, the map to from B is essentially the same as a present in OpenACC.
Yes. Yeah, the question was if that map to from acts like a present. Yes, in OpenMP it's always like a present or. So this would act, if it's present, it's taking the one which is already on the GPU. Yeah. So that is why these clauses here optional, since we defined it already in the data region around. Right. So same example for OpenACC, it looks quite similar. We have the p copy out statements in our data region around. We also have this initialization kernel here. We have the function call and then calling also the routines. Yes?
Pragmas for the second parallel loop. Instead of having that directly in the subroutine, could I also put them outside of the subroutine on the left there, in the main program?
Depending how your code is structured, usually you want to have the kernels around your loops. I mean, you specify there that you want to distribute the different loop iterations about your threads. So you need to specify the OpenACC or OpenMP kernel around the loops. I mean, you could also say you do a kind of parallelization around this function and then specify that you want to distribute these loops. You could also do that, but that's not the usual way you would go. Usually you really want to have a loop or maybe even in double, triple nested loops and parallelize that one.
So the loop should immediately follow the ACC parallel loop directive.
Yes, the parallel loop directives makes necessary that a loop statements follows. I mean, you can do an OpenACC parallel without a loop and then an OpenACC loop around the loop, but usually you do it in that way. So what else can you do, especially if you maybe want to interoperate with other programming models like CUDA? You can also expose the memory pointers to your code or to different parts of your code, which may be optimized in CUDA kernels. There are also CUDA implementations of different functionalities, libraries like cuPLUS or cuFFT. There's also a method called G2G, so doing a communication between two GPUs. But therefore, you really need the address of your data on the device. And this is what you can also provide using a directive. But you have to do that manually since the compiler don't do that automatically for you. And how you do that, you use in OpenMP the so-called use device pointer on the data you want to expose to. So let's say we want to call a function called dbl CUDA, so a CUDA function doing something with our data, which then maybe calls another function down here, which is CUDA optimized. You need to tell this function or the compiler on which data it can be acted. So the data is already on the GPU. You see that here we have a data region which makes the variable A available. Maybe you have some initialization, whatever, and then you say, okay, I need the pointer of this variable A, which then you can pass to your CUDA implementation, and this then can act on this memory on your GPU. And then you just need to close this data region here. So in OpenACC it looks similar. There it's called use device, and then you specified your data variable, but it's a similar behavior.
That example is not portable now to CPUs anymore, is it? Or
What do you mean with?
because if I don't compile with CUDA, then
Yeah, that example here you cannot run then on a pure CPU, right? Since it's CUDA. Yeah, right. But maybe you have your complex code and you realize that your trivial OpenMP port is not performing as you want, and you put much more effort in that, and you say, okay, I have this function here which takes 80% of my runtime. I really want to fine tune that one, so you maybe implement these small part of code into CUDA, calling that one when you have a GPU available. Then you can interoperate with all the rest of your application, which is then maybe just OpenMP parallelized, and this specific part then really fine-tuned in CUDA. Right. Questions to that? Then I have a kind of directive comparison. I mean, I already did some comparison between OpenMP, OpenACC. Here I just want to give you a list where you can compare the different statements. I mean, you will also get my slides then later on and can have a look what maps to what. So starting with the compute constructs, we have on the one side OpenACC, on the other side OpenMP. So we have the OpenACC parallel, and on the other side the OpenMP target teams, which just mentioned that you want to parallelize. Then we can also mention how we want to parallelize that. So in OpenACC we have the num_gangs clause. We also have the loop gangs, loop worker, and loop vector clause, where we can nicely map to the different layers of parallelization, saying it like that. So on thread blocks, maybe warps or vectors within the thread blocks, and then really threads within these blocks. Bit similar thing we have with OpenMP. So there you just say the distribute that we want to distribute it on thread blocks. We have the SIMDs. I mean, in contrast to OpenACC, we have just usually 2 levels of parallelization. So with the SIMD, then we parallelize within our vectors. For OpenACC, we also have the kernel directive. We don't have that in OpenMP. And then we have the data construct. So as we already saw, we have the data regions. We have the, here I wrote it in full length, so present or create, present or copy. So P, create, P, copy is the short term of that. And in OpenMP, we have the allocate to from clause. And as mentioned, up to 0, we also have just the copying in out statement for OpenACC, so neglecting if the data is on the GPU or not. It's always doing that one. Then we already saw the update clauses. So if you want to synchronize the data between CPU and GPU, we have the update from to or self device in OpenACC. And then we also have the unstructured data construct, so an ACC enter data or a target enter data with the related clauses, then allocate, copy, release, and delete. And then we also have the device pointers, what we had in the last few slides. And yeah, that's one more slide. Then we can also specify so-called separate compilations, where we can also tell the compiler that functions are just be created for a target device or not. Still one more, forgot that. Yeah, and the asynchronous constructs, I mean, we will come to that maybe tomorrow, maybe on Wednesday. So there you can also handle different kernels at the same time, which can be run and have different dependencies and so on. So we will have a closer look on that later on. And what I now want to mention is the general proceeding, what you, from my point of view, should do if you want to port your code. So what's here not mentioned, but maybe should be point 0, is really getting an overview of your code. Where is the most time spent within your code? So which is the really most compute extensive parts of your code? We get that usually by profiling. Then these parts should be in a simple kernel offloaded to the GPU. So just writing a simple kernel as we did it in the first example. Then we could maybe optimize this kernel, and then especially, which most often has the biggest effect, is optimizing data transfer. So reducing the amount of data which is copied forth and back to the GPU, since the data movement is the biggest bottleneck usually. There we will see we have different tools to do that. And then in another step, we can also use device acronously, where we can run different kernels, so streams and dependencies, defining that one. And if you want to go further and further, I mean, at a certain point, you could also implement certain kernels then in CUDA if you want, as already mentioned. So to conclude that sessions, from my point of view, device directives are an easy tool to port your codes on GPU, which is easily to maintain. It's also portable. Usually the compiler takes most of the work, so you just give the compiler some hints, what you want to port, maybe how it should be scheduled, how the data is moved, should be moved. And from my point of view, you can also easily swap between OpenACC and OpenMP. So if you see maybe nowadays it's more worth to port your code first to OpenACC, since in the 2.5 are more functionalities available than in the OpenMP 4.0. Then maybe at a later stage when maybe OpenMP has more features, I don't know, just a guess, you can easily port them to that one. Or you just start with OpenMP and do it the other way around. So it's easily the port, and yeah, the best thing before you start is really thinking of a metric to check your code, to check the validity of your results, so if all the results are correct, and which is also quite helpful usually is to have a track of your performance improvement. So if you port your code, having a reference how fast it runs just on the CPU, and then how you develop it with implementing your first kernels with your data regions and so on. So that we will, at latest, we will do that tomorrow, and I call it guided hands-on session. We do a short example together, porting more or less a whole application to the GPU, and we will see what different steps we will do and how this will perform. So with that, I would like to finish my presentation and wait for your questions. I mean, that's why you are here, to ask questions, right?
I'm still thinking about that example with the function call. Maybe could we get back to it?
Excuse me. I have to do that here again. No. Give me a second. Right at the end. So, you mean that one?
No, before.
So that one?
Yes, I think
Okay.
this one. So we already said that A should be moved to the GPU memory,
Right.
and B is kind of referring to the same thing.
It's, yeah, I mean,
Isn't
just
that-
another name for the same variable, right? Here we
So-
call this function with the variable A, which is then just called B, but it's the same memory, let's say it like that.
So isn't it redundant somehow that we again do some memory motion?
What do you mean?
So
So
we-
you mean that one here, where we have
What
the
if
map?
we leave it out? What would be
Yeah,
wrong?
that's what I mentioned with that data clause is optional. You
okay.
would not need it in that example here, since the data is already on the GPU, you use that one.
All right.
But for example, if you call that routine here from somewhere else in your code, which is not within the data region, you can be sure that your data scoping is correct. So for example, I mean, here it's to from, which is the default clause, but let's say you have here an initialization routine where you know you just need the result back of your routine, just as an easy example. And you just neglect that or do not define that here, and you call it from another part of your code, which is not within the data region, the compiler will automatically copy it to the GPU and back.
Mm-hmm.
So then, defining that here, for that initialization example, you just define a copy from A or B or whatever. You really verify, okay, for that routine, for that variable, I just need to copy back and not forth and back. So it's always overwritten, let's say overwritten in that case, that you use the memory or the data which is already on the GPU if it's on the GPU. But if not, you have specified it there, and for that case, you have the correct behavior.
And also, when we were talking about defaults, so when I have this OMP something for a loop, and I define some variables inside, will they always be private, right? Or not?
Depending on the variables, if it's scalar or an array, right?
So
Arrays are always shared, scalars are, depending on what version of OpenMP you use, they are shared or first private.
so they will become shared later, you said?
In OpenMP 4 they will be shared, in OpenMP 4.5 they are first private.
So
That's a bit
so
confusing.
then it means we were talking about defaults which are defined inside this parallel regions, and the variables which were defined outside, what happens with them?
No, if okay. If you have, for example, here another line acting on array C, I mean, it's like
Or
array here.
scalar D.
The array A is defined outside, but it's used inside the kernel. The compiler takes care about that the data which is used within the kernel is transferred to the GPU and back. So if you do not define that here within a data region or within a data clause of your kernel, the compiler takes the default case. So if it's an array, it copies forth and back.
And then it's potentially data race, maybe.
Data race between what?
Well, so imagine we have C outside and we do something with it.
Yes. I mean, it's like here having A outside and doing something with it.
Yeah, but we said that we want to load and unload A, but if...
Yeah, I mean, if we have C outside here and we do not define that in the data region and also not within the kernel, it's copied forth and back.
Okay.
So at the beginning, it's copying to the GPU, and at the end of the kernel, it's copying back the data.
And the same with the scalars, or not?
Yeah.
Okay.
Yeah. You just define the data scoping and the data region to really limit your data transfer, because that we will see that in more detail, but this is really the limiting part. So
And by
if you
default
use the default one, copying all the data forth and back, this slows down your code drastically.
Okay, thank you.
No, wait.
So I might have missed what you said before, but when you are calling when you're defining the B part, the do loop with the B inside this data clause.
This one here?
Yeah. Is it incurring an extra cost on the computation if it has already been on the memory before?
You mean calling the function, or?
Yes, it's already defined in the data region of in the main program, and then you are calling it again. You're saying OMP target teams distribute map to from B. Does it incur an extra cost to check if it is already on the?
So you mean if there is an additional overhead to check if the data is already on the GPU or not? That's a good question. At least it's not significant, so it's much better to just check if the data is on the GPU than copying. So copying would make much more overhead.
Okay. No, I was thinking in terms of multi-dimensional arrays, and if you just send one dimension and probe every time with this, then that could increase the cost. But as you said, if it is much less than copying it entirely, then yeah.
Internally, the compilers usually have a lookup table. So when you allocate the pointers, and then it has associated the region, so they quickly do a lookup and check if it is present on the device or not. So it's just a quick lookup. So it definitely doesn't cost you. I mean, copying around things will certainly cost you a lot.
We didn't see much C++, but I would suppose like the standard example would be where you just allocate a pointer with new, right?
Mm-hmm.
Does it work with STL containers out of the box?
No. I mean, that's what I mentioned. If you have really structures with maybe arrays in there.
I mean an STL vector or val array or array.
Not sure. No, I don't think so. With STL, you have to do it to convert it, right?
The short answer is no. I mean, because have you seen the code inside any of those STL vectors? Or I mean, so there you need a GPU kind of enabled implementation. So at least at the OpenACC there were discussions in supporting this, but it has several obstacles, like dealing with aliasing of pointers and all this stuff. So it's not that you can do a copy in or copy out of an STL vector. No, you can't do that at the moment.
But what will happen to it then by default? Because we learned that by default all the data will be copied and copied back.
Well, an STL vector is it's just a struct around the pointer plus some other fields. So at the moment you don't have the you don't have things like deep copy. So you cannot just pass this and an array bound, because the STL vector handle is not an array pointer. The thing you have, it's not an array pointer. It has an array pointer inside it, but it's not itself an array pointer.
So all this only works with the kind of usual C.
Yes, yes. But you can do your GPU aware containers. You could do them.
But there is no version of
No, currently no, is nothing readily available.
Just following up this STL issue. So assume we have the STL vector, and of course C++ compiler does not understand the semantics of it, but in the end it will generate access to some pointer inside the loop. Assume we have ACC parallel loop directive there, but nothing about copy in, copy out, and so on. So by default it will be copy in, copy out. So will it still work on GPU, perhaps with the extra copy in and copy out at the beginning and at the end, if I'm using just accessing the STL vector?
Accessing the STL vector from within the parallel region.
From within the parallel region, so C++ will just blindly generate some access of the index point.
Yes, but the operators in C++ are basic. When you use the square brackets are actually an operator. That's yes, which is a function. So this has, for example, to be.
It will be inline, in the end translated to some indexed access, some pointer-based access.
Yes, I haven't tried it, but.
CSCS will not be able to do anything with this anyway, because it does not know the size of the data array.
Yes, it doesn't know the size. And
the size is part of this vector structure, but C++ does not understand the semantics.
No, it doesn't. I mean, you have to pass it.
Expand
What you could do is probably you can get from the STL, you can get the raw pointer, and then if you have a function operating on that, then you can work as usual. But certainly, I mean, it won't work out of the box.
So
I mean,
the summary is that if you have some object-oriented code, say heavily using STL, then basically it cannot be readily parallelized.
Yes,
using
it can be. Yeah.
You have to extract it, you have to flatten it, and then you can do something. Okay.
Unfortunately, yes, not so far.
It's what I expected, because the main problem with C++ is there are no true arrays in C++. STL semantics is not understood by the compiler. And if you are using something like Blitz or something from the myriad of the third-party template libraries like Boost and so on, which implement their own arrays, again, we are at loss, because they are even not standard.
There's another question.
I have another maybe related question. We saw before briefly that you can specify the array indices you want to copy, like from to, right? Do these need to be known at compile time?
Not explicitly in numbers, but you can also define variables, yes.
Okay, so it can be a variable.
Yeah.
Yeah.
Basically must evaluate in, it need not be compile time. So just need to evaluate to an integer. I don't think if you can use functions, you may be able to use, but I'm not sure.
Not sure.
Had another question? So I guess we can go out for a break, for a coffee break, and then we come back after 15 minutes.
And then we do tools.
Tools and, okay.